So am I audible and can you see my screen?
Yes, sir, we can.
Okay. Okay. So any doubt on the previous part? Okay. So we'll continue our discussion with dimensionality reduction algorithm. So basically, depending on data type and the similarity measures we want to approximate, there could be uh, different dimensionality reduction algorithm exist. So I'll just okay. So so in random projection or feature hashing, our data types were real valued vector, high dimensional real valued vectors, and our similarity measure of interest is Euclidean distance and inner product, right? And the algorithm was random projection, and its improved variants and feature hashing, right? But the data can also be represented in different data type, not necessarily real valued vector. So in your like application domain, can you think of any other data type in which data is represented?
Strings.
Strings, okay. Data type is string. And again, so here when we talk about data type, we assume that our data size, data dimension is very large, and our aim is to compress that data into low dimension, such that from the low dimension one, we can closely approximate some interesting similarity measures. So in case of strings, what could be interesting similarity measure?
How many characters are different?
Yes, so that can be either Hamming distance or another
Dice.
form, edit distance, or maybe there could be some other distance measure. Okay, and any other data type you can think of? Hmm. So your data could be maybe say binary vectors, right? You can represent uh, bit DNAs in binary vector or categorical categorical data. And in this case, similarity measures could be, say, again, Hamming distance. Any other data type you can think of in your that you used in your like projects or applications? Like, data can be also considered as sets, right? And the similarity measures could be set intersection or Jacquard similarity. Have you heard of this term Jacquard similarity?
Yes, sir.
Okay. So that is again a popular similarity measure, and for that there exists some uh, dimension reduction algorithm that we'll see in the next class. And again, so there could be basically what I'm trying to say, like depending on the data type, the way data is represented, and the underlying similarity measure, there could exist different dimensional reduction algorithms, right? So there is no one algorithm that take cares of everything. So depending on data type and similarity measures, there exist different dimensional reduction algorithm, and also for these 2, 3, and 4, there are dimensional reduction algorithm. So in the remaining class, we'll see again we'll see one more dimensional reduction algorithm that takes real valued vector as input. And can you think of any other similarity measures in case of real valued vector? It's, so there is one which is called angular similarity.
Sir,
Or
is it cosine? Okay.
cosine similarity. Yes. And the algorithm that we'll see is SimHash or signed random projection. Okay. So cosine similarity or angular similarity, you can think of. So suppose if we have say two vectors x and y, right? And suppose the angle is say theta. So the similarity measure we can measure is cos of the angle between those input vectors. Or in some cases we can consider only theta as well. But reason of choosing cos is like it basically scales the value between -1 and +1. Okay. So when we already have, say, Euclidean distance for real valued vector, what is the motivation of going for another similarity measure? Any idea?
Euclidean doesn't scale well for high dimensions.
It scales well, but
I mean,
so what I'm trying to say, like uh, Euclidean distance does not correctly captures cosine similarity, right? So we can, for example, say if we have say two data points like this. So x is this, and y is very large. So here there, so you can scale like y, um, to more. So, and so basically here their cosine similarity is small, like cosine similarity is high, like they are very similar, but the Euclidean distance is very large. Right? So they are similar as per cosine similarity, but as per Euclidean distance, they are very far apart. Right? So in some applications, Euclidean distance could be appropriate similarity measure, but in some application, cosine similarity could be appropriate similarity measures. Right? So Euclidean distance doesn't capture all the essence of the data, the way data is represented. Okay, so does this make sense? Okay, so we'll see this algorithm that takes input as high dimensional real valued vectors and output low dimensional vectors that approximates cosine or angular similarity. And we'll see that the compressed vector are binary vectors. And using those binary vectors, we can estimate the cosine or angular similarity of the original vector. And this is very popular algorithm, and it was invented by Moses Chariker in 2002 when he was doing internship at Google. And this is very popular result, and Google uses some improved variants of it still in their indexing application, indexing based application. It's, I think, more than 2600 plus citations, and the paper name is Similarity Estimation Techniques from Rounding Algorithms. Appeared in stock. Okay, and the idea is very simple. Right? So okay, have you heard about this algorithm before, signed random projection or SimHash?
No, sir.
Okay, so the idea is very simple. So basically, suppose we have say two vectors, say u and v. Their angle is theta. So basically, given pair of vectors u comma v in Rd, what we do, we take a random hyperplane. Okay. We take a random hyperplane and we see if it separates u and v. Okay. See if separates u and v. Right. So for like simplicity, we focus on the first two coordinate because like you can essentially okay. So what is the probability that so basically we what we'll do, we'll take a random hyperplane, maybe like this, or it could be like this, it could be like this. Okay. So now what is, we want to calculate the probability that a random hyperplane separates u and v. Right. So since we are taking random hyperplane, it could lie anywhere. Like random hyperplane passing through origin. You can, for simplicity, you can think of this as origin, and we are taking random hyperplane passing through the origin. Right? It could be here, it could be here, it could pass separates u and v. So what is the probability that it separates?
Sir, theta by 360 degree?
Partially correct. Just think more. So yeah, so since this is like so for simplicity, we focus on the first two coordinate, right? Like this is symmetrical in this side. So
So theta by 180.
theta by 180, right? Theta by pi, right? Theta by pi. Is this clear to everyone?
Sir, why only upper half?
Okay, so suppose if your uh, vectors are like this, and so basically it's symmetrical in both way. Like so if you take random hyperplane, it separates u and v. It will be 2 theta upon 2 pi, and so it will be kind of theta upon pi. Right? It doesn't matter. Just for clarity of pictorial clarity, I like we focused on the first half, but it doesn't matter.
Yes, I got it.
Okay. So now we need to somehow capture this in form of say some hash function. Okay. So okay, so the we'll use the following as our hash function. So So we'll let R be a random vector. So that and each feature of Ri sampled from again normal distribution with mean 0 and unit variance, right? And our hash function is basically we calculate the dot product between the vector. So we want to calculate what is the compressed representation of u using this vector r, and we are capturing it by the hash function hr. So this is our hash function. So we calculate the dot product of u and v, and if its sign is non-negative, the hash value is 1. Otherwise, if and 0 otherwise. Right?
Sir, can you go over this once again?
Okay. So basically, our intuition of designing such algorithm is basically we'll take uh, random hyperplane, and if random hyperplane, basically the probability that random hyperplane separates u and v is theta by pi. I hope this part is clear.
Yeah.
Now our aim is to basically capture this theta, right, without explicitly calculating it. So what we are doing, uh, we are taking a random vector, okay, and we are taking the dot product of the random vector with our input vector r, right? And if the sign, its sign is basically sign of the dot product is non-negative, our and basically using r, we are designing a hash function which takes the input vector and takes the input vector and output either 0 or 1. Okay, so and our hash function is basically we take the dot product of u and r, and if sign is positive, the resultant value is 1, and it is 0 otherwise. So this is the algorithm. Okay.
Yes, sir. Thanks.
Okay. So now for 2 data point, probability that HRU is not equal to HR of V is what?
When the vector we choose is between those two.
Yes. Yes. And what is that value?
Theta.
Okay. So we want to calculate the probability of that. Probability that HR of U is not equal to HR of V is theta by pi. Right?
Yes, sir.
Is this part clear to everyone?
Yes, sir.
Okay.
Can you please repeat once again?
Okay. So basically, our intuition is we'll take a random hyperplane, and see if it separates u and v. So if the so as our hyperplane is random, probability that it separates u and v is theta by pi. So now this gives us some intuition to design a hash function using which we take our input vector as input to that function, and it outputs certain quantity, say 1 and 0 in this case. So our hash function is basically we take a random vector rd such that each coordinate is sampled from normal distribution with mean 0 and unit variance. And our function is we take dot product of input vector with the random vector, and if sign is positive, non-negative, then the value is 1 and 0 otherwise, right? So now we want to calculate if we use the same hash function for two data points, say u and v. So what is the probability that their sign is different? So their sign will be different when that hyperplane separates u and v, right? By this image, you will be able to convince yourself. So that is theta by pi, right?
Yes, sir.
Okay. So now what we are doing? So here, in a way, you can think of here we have say vector u. So here we have vector u, which is u1 to ud, and we have vector v, which is v1 to vd. And after applying this hash function, say hr, we got a binary value, either 0 or 1, basically 0 or 1. Or maybe I should write it like this. So we are getting either 0, either 0 or 1, or both. Then our claim is their value is different, is probability that their value is different is equal to theta by pi, right? So basically, so in this dimensionality reduction algorithm, our input is real valued vector and our output is a digit, either 0 or 1, right? So does this make sense?
Yeah, yes, sir.
Okay. So what we can do, we can just choose several such hash function, right? And we can repeat this process, right? So if we repeat this maybe k times, so what do we get? So our input is same, so we'll get a binary vector, I'm denoting it like this, of size k, right? So this is corresponding to u and this is corresponding to v, which I'm just denoting it as say u prime and v prime. And by computing the Hamming distance between u prime and v prime, we can estimate the cosine similarity or angular similarity, right? So does this make sense?
Sir, when we repeat
So
with multiple hash functions, we
yes,
will get a vector of zeros and ones, right?
yes. So that's what I have written. So maybe I'll just for clarity, I'll write it like this. So repeat this k times independently using different different r, like, right? Each time we generate a different r. So corresponding to u, we'll get a binary vector of size k, right? So it will have 0, 1. So this is corresponding to U, and this is corresponding to V.
So sir, here our R is equivalent to hash function, right?
Yes, so basically R determines our hash function, so that's why in subscript we have written R.
Okay.
So this is, suppose I'm denoting this as say US, which is a binary vector in k dimension, and this is VS, which is a binary vector in k dimension. Right? So the Hamming distance, right? So is this part clear? So if we repeat k times, each time we'll get uh, one coordinate of the one coordinate of the reduced dimension vector. Right? So yeah, tell me.
I was just saying yes, sir.
Okay, so Hamming distance between US and VS gives estimate of angular cosine similarity. Okay, so how we'll do it? We'll just see in a minute. Okay, so okay, so I'll use, just for sake of analysis, I'll use one indicator random variable. Say so I'll use one indicator random variable, say x1, that takes value 1 if h r1u h r1u is not equal to h r1 v and 0 otherwise. Okay, so just basically we are trying to capture this thing via an indicator random variable. Okay, so we choose, we are repeating this k times, so each time we use different random vectors. Right, so where this ri is from. Ri is, okay, so Ri is d-dimensional vector whose each coordinate sampled from normal distribution with mean 0 and unit variance. Okay. So again, what is expected value of x1? Expected value of
1 by k.
No, no.
Sorry,
So
sorry.
expected value of random indicator random variable is the probability of the corresponding event it is capturing, right? So so just keep this thing in your mind, like when you need to calculate expected value of a random indicator random variable, just see what event it's capturing and what is the probability that when it will take non-zero value. So it is probability that h of hr1 u not equal to hr1 v, right? So essentially, if we just expand this in the standard expectation notation, so basically value, so it takes two value, 1 and 0. So value 1 into corresponding probability plus value 0 into the corresponding probability. So what will be the probability here? HR1 U equal to HR1 V. So since this is 0, so this term will not contribute. So that's why we focus on this part, right? So what is the value? This value that we have seen just now.
Theta by pi.
Theta by pi, right? Okay, very good. So now we are basically using k such random vector, and corresponding to each we define, say, k such random variable, indicator random variable, say x1 for x1 corresponding to r1, x2 corresponding to r2, x3 corresponding to r3, dot xk corresponding to this rk, right? So we are trying to define a new random variable which captures the angular similarity, right? So this x is our new random variable, and we are scaling it by pi by k. Okay, so this x is our new indicator random variable. So okay, so now what is the expected value of x? It's pi by k into I from 1 to k expected value of xi, right? Okay, so this is pi by k and summation I from 1 to k. So this E of xi is theta by pi, right? So so this will be pi by k into k theta by pi. So finally we get theta. So this E of x is theta. Okay, so is this part clear? Right, so essentially we just uh, repeated the thing k times, and corresponding to each event we designed an indicator random variable, and our final indicator random variable is we are just adding up all those k indicator random variable and scaling it by pi by k, right? So and if we take the expected value of our new new random variable, then it is theta, basically the angular similarity. Okay, so is this part clear?
Yes, sir.
Okay, so now let's try to calculate the variance, and it's again very simple. So variance of x will be what? So we need to calculate variance of pi by k sigma xi I from 1 to k, right? Which is Okay. Now, can you help me calculating this variance? So variance of AX is what? A square into variance of X. Right. So this will be pi square upon K square, variance of sigma Xi. Okay. So now I'll apply the definition of variance over here. So this will be expected value of sigma Xi, I from 1 to K square minus E of sigma Xi, I from 1 to K whole square. Okay, so this term is what? This term we have already calculated. So this term is what? And this pi square upon K square is
Theta square
theta
by pi
square.
square.
Theta by pi square.
E of Xi is okay. So this will be okay, so E of sigma Xi for is theta square really, or
Just theta square, no, sir.
theta square by okay. So let me just calculate it explicitly. 1 second.
So we calculated expectation of X, right?
Huh?
And
Yes.
it's just whole square of that, right?
Yes.
No,
So
there
E
is
of
one.
Xi. So we are summing it K times. So it will be sigma E of Xi I from 1 to K, right? And it's square. So expected value of Xi is what? Expected value of Xi is theta by pi, right? So it is summation I from 1 to K theta by pi whole square. And this is basically the same thing we are adding up K times. So it will be K theta upon pi whole square, right? So this is what we get. This is our second term, right? So is this clear? Yes or no? So this is basically this term we need to calculate by linearity of expectation. We take the expectation inside. Expected value of each term is theta by pi, and we are summing it K times. So it will be K theta by pi, and square is anywhere there. Okay, so now we have second term or first term. So this is our second term. This is second term. This is first term. Okay, so now let's try to calculate the first term, which is sigma Xi from 1 to K whole square. Okay, again, so we open this square thing. So it will be sigma Xi square I from 1 to K plus sigma Xi Xj I not equal to J. Right? So I've just opened up this expression. Okay. So now we'll just, by linearity of expectation, we'll have I from 1 to k, and so is this part clear? So now what is the value of xi square, given that xi is indicator random variable? Yeah, tell me. What is the value of xi square if x is indicator random variable?
Same as xi.
Yes. So it is same as xi. So so this will be I from 1 to k and E of xi plus, so again by linearity of expectation, I not equal to j. So here xi and xj are designed using two independent hash functions, right? Because for each time we choose a completely different Ri. So these are xi and xj are independent to each other. Or IID. So we can do this. Okay, so now we'll put the values. E of xi is theta by pi, and we are summing it up k times, so it will be k theta upon pi. And this is I not equal to j. So for this we have again theta by pi, and for this we have theta by pi. And how many terms will be there in the summation? I not equal to j, I and j from 1 to k. K into k minus 1, right? So this will be our first term, and if we, so maybe this is equation 1, this is equation 2. By putting this in, this may be equation 3. So we get variance of x is what? Pi square upon k square. And this is the first term, k theta by pi plus k into k minus 1 theta by pi whole square minus this is the term that we need to subtract, right? So this is this part, k theta by pi whole square. Right? So I've just I didn't do anything fancy, I just put the corresponding values. Okay, so is this part clear? So now after doing some calculation, basically just expanding this term, so we left with k theta by pi minus, so basically this consists of two terms, k square theta by pi whole square minus k theta square by pi square. So the first term will cancel out with this one, right? Or maybe I'll just do it. K square theta by pi whole square minus k theta by pi whole square minus k theta by pi whole square. So this will get cancelled out with this. And we can take k outside common from both of these terms. So this is pi square by k square into k. So this is theta by pi. This is theta by pi whole square So we get theta pi minus theta by k. Right. So just to summarize, expected value of our estimate is unbiased, and whereas its variance is theta pi minus theta by k. Right. So any doubt on whatever we have covered so far? Yes or no?
Sir, we calculated the expectation for this new random variable, right? Yeah, there.
Yes. Yes.
So I mean, why didn't we directly take theta as expectation of x in the variance calculation?
Where?
So can you go one or two lines lower than this? There. So in the third equation,
Yes.
the second term is expectation of x whole square, right?
Expectation of sigma xi whole square. So I've just calculated
Okay,
it.
okay.
So by
Okay, so the k by pi is missing there and we scaled for that. Okay, good, thanks.
yes, yes. So basically, so x1 is our original random variable, and if we calculate the variance of, okay, so I'll just write it here. Okay, so here if we summarize, E of x1 is theta by pi, and if we calculate variance of x1, it is, you can verify, this will turn out to be theta pi minus theta upon pi square, I guess, if I'm not wrong. Mm, wait. Okay, 1 second. Theta pi minus. Okay, 1 second. So here we can define a new random variable. Say maybe I'll just say xo. Okay, so here what I'm doing, design. Suppose I design a new random variable, say xo, which is pi of x1, and if we calculate expected value of xo, so that will be basically theta by pi into pi, so that will be theta, and if we calculate variance of xo, it is theta pi minus theta. Okay, so just ignore this thing. Okay, so the idea, like, so why did we repeated it k times? Just to reduce the variance, right? So here our new random variable x0, its expected value is theta, and but its variance is theta pi minus theta, right? So just to reduce the variance, we repeated it k times and designed a new random variable x and scale it by pi by k. So after doing this, again, our expected value of our new random variable is theta, but its variance is scaled by k. Right? So accordingly, we can choose the value of k so that our variance is within the limit that we want. So that is the motivation of repeating it k times. Okay, any doubt? Okay, so now we can also see this SimHash as matrix multiplication algorithm. Okay, so suppose our say data set is X of size say D cross N. So this is our X input. What we used to do in case of random projection, we used to generate a matrix of size K cross D. This is random matrix whose each entry say Rij is sampled from normal distribution, right? We multiply these two matrices and the resultant matrix is of size K cross N. So this is R, this is X, so this is Rx, right? So this is what we used to do in case of random projection or JL lemma, right? So here, what do you think we need to do so that the resultant thing is works as SimHash? Okay, so suppose this is say some vector u, and this is say vector this, and their dot product is maybe somewhere over here. Right? So if you, so suppose this is say vector r, this is vector u. So this vector is what? This vector is r into u, dot product of r and u, right? And in case of this SimHash, what we are replacing it with, either 0 or 1, right? So depending if it is 0, we are putting it 1, and 0 otherwise, right? So basically we are just whatever value is there, we are just replacing it by 1 and 0 depending on its sign, right? So is it easy to see? So in our SimHash algorithm, what was our SimHash algorithm? We take inner product of u and r, and based on the sign we assign the value as either 0 or either 1 or 0, right? So we just wanted to see if this can be viewed as matrix multiplication algorithm. So suppose this is our random matrix whose each entry is sampled from Gaussian distribution, and this is our input, and their size is k cross d and d cross n respectively. So suppose if we focus on these two vectors here, this vector r and this vector u, So they are contributing to maybe this entry of the matrix Rx, right? In case of random projection, we just used to take this value as it is. But in case of signed random projection, we are just replacing it by either 0 or 1, depending on the sign of dot product between U and R, right? So that's why it's called signed random projection, right? So is this part clear?
Yes, sir.
So the standard random projection algorithm approximates Euclidean distance and dot product, and the signed random projection algorithm approximates angular similarity and cosine similarity. And again, the running time is order ndk, and the space is order kd to store matrix R, right? So in layman term, you can just view this signed random projection as random projection or SimHash. So they are basically two names of the same algorithm. It's nothing but random projection plus sign of the corresponding entries. That's all. Okay, so any questions until this point?
So both SimHash and signed random projection are same, or
Yes,
is it-
yes, same. Yeah. So they are basically the same name of two different name of the same algorithm.
okay.
Okay, so all right, I'll stop here now. So if you have any question, just feel free to send me an email.
I have a question regarding